And I wanted to just sort of review something from yesterday. When you have a long straight wire carrying a current in some particular direction, the magnetic field a distance r away from it will end up having a strength of B equals mu naught I over 2 pi r. So that's the strength of it. As far as the direction of it goes, if you're looking down the wire so that this X represents current going into the page there. Oh, where's my circle drawing gizmo? The magnetic field out there at any given point. Okay, point your thumb in the direction of the current flow and your fingers can curl in the direction, thumb of your right hand, your fingers can curl in the direction of the magnetic field. So here you have I going into the page. This will be B, and it forms, for current going into the page, it'll form clockwise circles around there. If you have the current coming out of the page, which you signify a little circle with a dot here, you get the magnetic field going in the opposite direction. And those are some things we're going to consider here today before too long. But in that case, B goes that way. So, and that's a current coming out of the page. So you use the right-hand rule again. You can point your thumb in the direction that the current's going, and your fingers will curl in the direction that the magnetic field goes. And you get these nice concentric circles, but it does get weaker with 1 over r as you move farther away from the wire. So this would be the direction r in either case. So anyway, that's what that is. And we'll be using that some today. We're going to finish the problems that were on the handout that I gave or made available yesterday. I think there are 3 actually, although one of them was printed way too small to see, so I blew it up. And then we'll move on and consider the forces that parallel currents can exert on each other. And when I was a student at the university, in grad school at the University of Minnesota, I taught a lab I think it was a Saturday morning or something. And I went to college on the Minneapolis campus, and this was over at the St. Paul campus, which was 4 miles away, but I actually lived halfway between them. But anyway, in this lab, they had a demonstration set up with 2 parallel wires hanging down. It's kind of a neat thing. And they were just hanging parallel to each other by strings. And then you could throw a switch and you would put current into the thing. And I think it actually used a car battery. So it was a 12-volt battery, and it would have been a lot of current in the thing just because it had very little resistance. But you could make the current go either parallel, or you could reverse some connections on one of the wires and make it go so the current in one went this way and the current in another one went the other way. And you only closed the switch for a brief instance, but it was enough to see the direction of the forces that those 2 parallel currents exerted on each other. And it was kind of a neat thing, and we'll talk about that today. I'm really tempted to try and duplicate that setup sometime, but not sure just how I would do that. So let's start with one of the ones from yesterday. And this one looks like it could potentially be very hard, except turns out it's not. And we'll see how it is. You have 4 very long current carrying wires in the same plane. So you could just imagine them laying on this sheet of paper here. And they intersect to form a square 40 centimeters on each side. So this distance here is 40 centimeters. but turns out we're not going to need that. And so that distance would be 40 centimeters, but this distance is going to be 40 centimeters as well. And then we want to know something about the very center. Okay, it says find the magnitude and direction of the current I, that's the current in this wire here, so that the magnetic field at the center of the square is 0. Well, in every case, the magnetic field at the center of that thing is going to be, whoops, I want B is going to equal mu naught times I, where I is whatever current is in, like, say, this wire, and then divided by 2 pi r, where r is going to be the distance from the wire over to there. Well, it turns out for all 4 of these wires, this one, this one, this one, and this one, r is going to be the same. And you want the magnetic field at the center to be 0. Okay, well, here's how it can happen. Let's let into the page be negative. Is the negative direction. And then I'm going to number these wires. This will be wire number 1. This will be wire number 2. This will be wire number 3. And then this one down here is 4. Okay. Well, the magnetic, we don't know the current in wire 2 yet. And so I'm not going to worry about that one. But the magnetic field strength from wire 1, if I point the thumb of my right hand in the direction of the current in that wire, my fingers will curl in this direction. And that means the magnetic field of wire 1 is going to go into the page. That's negative. And so B1 at that point, I'll just call this point P, is going to be negative mu naught I1 over 2 pi, and I'll just call it R. And for all 4 of these things, R is going to equal 20.0 centimeters or 0.200 meters. But turns out we're not even going to need that because it's the same for all of them. Okay, well, what about B3? We know that current. Its current is going in that direction. It's not so easy for me to show it unless I rotate the page. Current 3 is going that way. Right-hand rule on this side of that wire, the magnetic field is going to be into the page, so it's another negative 1. And so it will be minus mu naught I3 over 2 pi r. And then B4. Okay, finally, if I point the thumb of my right hand in the direction of the current flow on that side of the wire, my fingers would be coming up out of the page. So this is a positive one finally. So it'll be mu naught I4 over 2 pi r. And then for B2, it'll be mu naught I2 over 2 pi r, but I don't know the direction yet. But I have to have the sum of these things equaling 0, and I should be able to come up with some way to add this up and make it go to 0. For now, I'm just going to worry about the magnitude of the current for I2. If I look at what I've got here, I have a 10 amp current that is producing a magnetic field here into the page. I have an 8 amp current that's also producing a magnetic field into the page. And then I've got a 20 amp current that's producing a magnetic field out of the page? Well, I've got basically 18 amps worth of negative magnetic fields and 20 amps worth of positive magnetic fields. That leaves me with 2 amps worth of positive magnetic field that I have to counteract. Or I can think B1 plus B2 plus B3 plus B4, I want to equal 0. Well, if I solve that for B1 or B2, excuse me, it'll equal the negative of B1 plus B3 plus B4. And again, this is only at that point P that this is working. And if I look at these things, they've got a common mu naught over 2 pi r. So I'll just take mu naught over 2 pi r out here. And what I have inside there is going to be, let's see, I'll have minus I1, minus I3, and plus I4. Okay. And so what am I going to get out of there? Well, I can just take the magnitudes of these currents now. I1 this is minus 10 amps. This is minus 8 amps. And this is plus 20 amps. Altogether, that gives me 2 amps left. And so B2, that magnetic field, is going to be minus mu naught over 2 pi r and times 2.00 amps. So, okay, I have to have 2 amps flowing in wire 2, and I have to have it in such a direction that it counteracts this one, which is actually winning. Okay, well, that magnetic field is going to be up out of the page, so I need to have the magnetic field of B2 has to point into the page, which means the current in this one has to be going downward. There's my right-hand rule again. And so I2 has to be going in that direction, and it'll have a magnitude of 2.00 amps. Okay, and it's down in the drawing. So I didn't actually have to calculate any magnetic fields because I was able to factor out the things that would require calculation. And I was able to just do it with comparing it to these other things. So, and that was the key equation, magnetic field of a long straight wire. Okay, this is one that kind of complicated, actually. Ignore this bottom part. That's the one that I had to blow up bigger to do today. But we have 2 long, straight, parallel wires that are 1 meter apart, so 1.00 meters apart. Upper wire carries a current of 6.00 amps into the plane of the paper. And, okay, so that's the case. What must be the magnitude and direction of the current I2 for the net field at point P to be 0? So at point P, let's see, I think I'll let X point to the right and Y point up in that direction. Not that it matters a whole lot, but we'll see what we can get here. Oh, this is the right angle here. I just noticed, although we don't need it for part A. But at point A, or at point, why did I say B down here? It's point P that I care about. All right, well, I1 is the one that I know, and so I could say that B1 is going to be, okay, its current is going into the page, and B1 down here at point P is going to point to the left. Okay, and I got it by pointing my thumb in the direction that the current is going in I1 and then curling my fingers. And down here, they'd be curling to that side. And it would be mu naught I1 over 2 times pi times the distance from I1 down there is going to be 1.50 meters. Okay, and that would be in the minus I hat direction. Now, if the magnetic field down here at point P is to be 0, that means that I2 is going to have to produce a magnetic field that counteracts this thing, and it would point in the plus I hat direction. So B, or B2, is going to have to equal B1. Actually, it has to equal the negative of B1, and this could have an arrow on it. And so it'll be, but it's going to be mu naught I2 over 2 times pi times, for B2, it's only going to be 0.50 meters away. So 0.50 meters, and that's going to be in the positive I hat direction. Well, I can just replace B1 down here with mu naught I1 over 2 pi times that thing and compare their magnitudes. I know which direction the current in I2 is going to have to go. It has to be coming out of the page here. But I can set these two expressions equal to each other. And mu naught I1 over 2 times pi times 1.50 meters is going to equal, in magnitude, mu naught I2 over 2 times pi times 0.50 meters. Yeah, well, that's as much sig figs as I have on those things. Oh, that's yeah, that is 0.50 meters. I think I get about 1/3. So I2 got mu naught over 4 pi's on both sides, and or 2 pi's. So I don't need those. Multiply that out from underneath, and I2 is going to equal 0.50 meters over 1.50 meters times I1, or 1/3 of I1. And it says I1 is 6.00 amps. I will get 1/3 of that, which is, I've only got 2 significant figures left. They should have called that 0.500 for me, but that's all right. 1/3 of I1 ends up being 2.0 amps to 2 significant figures. So that's part A on this thing. So I have that. Now, if condition A happens to be met, what are the magnitude and direction of the net field at point Q? Okay, well, for I1, it's got a current coming out of the page. It'll make a magnetic field up here that's pointing to the right, or excuse me, pointing to the left. Okay, got to get that. So this will be part B. And I'll say that this is going to be B sub Q, except it's B1 comma Q, I guess. And it'll be in the minus I hat direction, but it'll be mu naught I1 over 2 times pi times, this time it's 0.50 meters, to that part. And it'll be in the minus I hat direction. And then B2 at Q is going to equal, well, let's see. I2 was, I didn't state which direction it happened to be going. I2 was into the page. And down here, I2 point or B2 points in that direction. But up here, it's going to point to the right. So B2, it's going to be mu naught I2 over 2 times pi times 1.50 meters is how far it is from I2 up to there. And that'll be in the plus I hat direction. So it would be the sum of these two things, and I'm just going to bring in a blank piece of paper to finish working on this thing. Oh, and I know that I2 happens to be 1/3 I1. So if I do just B sub Q, the total, it's going to equal B1 of Q plus B2 at Q. So I'll have, let's see, mu naught I1 over, and I guess we actually have to calculate a magnitude on here finally. 2 times pi times 0.50 meters. And that's in the minus I hat direction, plus mu naught I2 over 2 times pi times 1.50 meters. Yeah, and I2 was 2 amps. So eventually I'll plug that in, but that's in the positive I hat direction. So if I factor stuff out here, I'll get mu naught over 2 pi. Whoops, that's out front. Times minus 6.00 amps over 0.50 meters plus 2.0 amps over 1.50 meters. And that's going to be in the I hat direction. This looks like 12 amps per meter, minus 12 amps per meter plus, let's see, 1.33 amps per meter. So, and it's just 2 sig figs on here. So this thing gets kind of inconvenient on the significant figures, but plus 1.33 amps per meter, and that's in the I hat direction. So we can finally do a little bit here. Whoops, this is mu naught. Remember, mu naught is 4 pi times 10 to the minus 7th. Let's see. I think it's Tesla meters per amp, if I remember right. Check me on that if I'm not. Looks like amps per meter. Yeah, I'll end up with that divided by 2 pi. And then times, this actually ends up being minus 11 to 2 significant figures, and that's amps per meter in the I hat direction. So this gives me a 2 times 10 to the minus 7th times minus 11. So it'll be minus 22 times 10 to the minus 7th Tesla in the I hat direction. So that's what it would be at that point, B sub Q. And then they also have you calculate the magnitude of the net field at S, which is not along a line with these things. Well, let's see. We can kind of figure out the direction. Let's see. That's going to be weird. the field due to I1 going into there, it's actually going to point straight down that way. So that would be B1. Maybe I should draw a bigger picture for that. The field of 2, yeah, this is kind of an interesting little diagram now. Oh, I noticed that this is 0.6, this is 0.8, and that's 1. This is a 3, 4, 5 right triangle. So S is this point right here. This is wire 1, this is wire 2, or current 1 and current 2. So here is, I forgot the name of that point, S. The magnetic field of wire 2, let's see, current 2 is coming up out of the page. So B2 will point in this direction. And the magnetic field of wire 1, which is into the page, hard to crank your right arm in the right direction sometimes, but it's going to point down here in that direction. So this is going to be kind of a messy vector problem to try to figure out, but I think we can do it. And we had a 3, a 4, and a 5 here. I could figure out each of these angles. Call this theta 1. No, I'll call it theta 2 because it's next to that one. And I'll call this the theta 1. Theta 1. Let's see. Okay, theta 1 will equal the inverse tangent of 4/3. And I'm just getting magnitudes of these angles. I'll figure out the components later so that they have the right signs. But $53.1 degrees. And I do have enough sig figs to keep that many, that precision on there, because this is actually 0.600, this is 0.800, and this is 1.00. So 3 sig figs all around. This will be theta 2 is actually it ought to be 36.9 degrees, but it's also the inverse tangent of 3/4. So let's just see if that's what we get. It better be, unless I've got something screwed up here. Yep, 36.9 degrees. So now I've got a chore trying to express these things in sine or in I hat j hat form. And somewhere back, I already picked x to point to the right. So, and y to point to the left. So B1 is going to have negative components for both I hat and j hat. Actually, this will equal, this will be theta 1 here. So it would be magnitude of B1 with a minus sign, cosine of theta 1 in the I hat direction, and it'll be minus the magnitude of B1 times the sine of theta 1 in the j hat direction, and B2 will equal, that's theta 2, this is 90 minus theta 2, that makes this theta 2 again. B2 will equal the magnitude of B2 going to have a minus sign on the x component times the cosine of theta 2 in the I hat direction. It's got a positive j hat component plus b2 times the sine, that's supposed to be a theta 1, of theta 2 in the j hat direction. So this is kind of messy, figuring out these things. However, we've got the hard part done, actually, just setting all that stuff up. This is a 3-page problem all by itself. So figuring out the magnitude of B1, it's going to be, well, it's a long straight wire, so it's mu naught I1 over 2 times pi times, somehow going back to this diagram, 0.60 meters, 60600 meters is how far away we are. And then magnitude of B2 is going to equal mu naught I2 over 2 times pi times, I have to go back to my diagram, and it's 0.800 meters for that one. Okay, so this will make it possible to determine each of those magnitudes. And then the expression that we got over here, you take those magnitudes and multiply them by the cosine of theta 1, sine of theta 1, and cosine of theta 2, and the sine of theta 2. And then you add the things together. So it's kind of arithmetic from this point, but getting to this thing was the hard part. This is a complicated vector problem, and we haven't done those for a while, so it would be good practice for you to do this and figure this out, finish it off on your own. Okay, the last problem on this set is one that I had to blow up again, but here's what we've got. We have 2 long parallel wires hanging by 4 centimeter long cords from a common axis. The wires have a mass per unit length of 0.0125 kilograms per meter and carry the same current in opposite directions. What is the current in each wire if the cords hang at an angle of 6 degrees with the vertical? Holy cow. Well, make a sketch first. Let's imagine this is a ceiling, and then here's a wire, a cord that's holding one of these things. Let's see. Oh, they're hanging from a common axis. Okay, so that means, forget this, they look like this. Here's one of the wires, and here's the other support string or something. And it says they carry the same current in opposite directions. So one of them is going to have the current going into the page. The other one's going to have a current going out of the page. What's going on with that? Why would they repulse each other? Well, let's figure this out. First thing I want to do is just imagine that we have a wire here, and it's got a current going into the page. What about its magnetic field? Okay, point my thumb in that direction and my fingers will curl in the direction of the magnetic field for this wire, and the magnetic field will be concentric circles, not what I drew, and going in the clockwise direction. Now let's imagine that we have another wire over here also with its current. So this will be I1, this will be B1, and this will be I2. Okay, now what about its magnetic field? Well, thumb in that direction, I'll get a magnetic field for this one going in that same direction, but look what's going on here. On this wire, I'm going to have it be acted on by a magnetic field that's pointing down, and a particular length of this will have a force on it that looks like IL cross B1. Okay, that will be the force that's acting on wire 2. And that'll be F of 1 on 2 is what I'm going to call that. What about the force that 2 exerts on 1? The force of 2 on 1 will equal, well, and by the way, this is the total force on some length L of the wire. We're actually going to change that and look at force per unit length to try to compare this thing. But the magnetic field of B2 points up. Oh, the direction of this force. Okay, L cross B1. L is a vector that points in the direction of the current flow. So for that one, it's going to point that way. L cross B1 is going to be to the left. Let's go to the force of 2 on 1. Well, the magnetic field of number 2 is actually going to be pointing up here, and IL cross B2 for this wire, L will be in that direction. I curl my fingers in the direction of that thing, and the force that 2 exerts on 1 is that way. This is the F2 on 1 that way. This will be F1 on 2 is going to be to the left. When the currents are parallel, the wires attract each other. And it'll end up being, whoops, force of this would be I1. Nope, it's I2 L cross B1. Now, in the situation we're looking at, L and B1 are perpendicular to each other when you've got these parallel wires. And so that magnitude of 1 on 2 can just be written I2 LB1, or I can figure out F1 on 2 per unit length, and that's the way it's often written. It'll be, let's see, just I2 times B1, but B1, this is a long straight wire, is going to be mu naught I2 over 2 pi r. Well, let's call r the distance between them. And they developed this in the book. So it ends up being mu naught I1 I2 over, and somewhere, I tossed my notes upside down. 2 times pi times r actually is what it ends up being. And it turns out that the force of 2 on 1, well, it's actually the third law partner of this. It ends up being, oh, that's what I was doing. Force of 1 on 2 per unit length. Per unit length is the same thing. Mu naught I1 I2 over 2 pi r. Now, this is just the magnitudes of them. In this case, the force of 1 on 2 is to the left. The force of 2 on 1 is to the right. So this is something that we can use to try to figure out the solution to this problem. So let's label these things. We've got current going in opposite directions, and so I'm gonna, that one will work. Okay. I'm going to label this as 1 and this as 2, wire 2 that is, and this curved arc here is going to be the magnetic field of wire 1. This one is coming out of the page, so let's see, just center it there, pick a hole that matches up pretty good. This one works okay. Okay, this would be B2. It's the magnetic field produced by wire 2. And so that's what I have. Now, the forces that are on these things, well, current 2 is coming out of the page. If you imagine poking your fingers in that direction so you can curl down in the direction of that magnetic field, here we'll have the force of 1 on 2 is to the right there. And the magnitude of that force per unit length, 1 on 2 per unit length, is just going to be that mu naught I1, I2 over 2 times pi times r, where r is going to be, again, the separation between these two things. And then if I do something similar, oh, that force is to the right. Okay. Oh, it says I1 and I2 are the same. Same current in opposite directions. All right, that'll keep things a little bit simpler. What else do we want? Oh, let's figure out the one on this one. This one, the current is going into the page. B2 at this location is going to point straight down, and so we'll have the force that's on this one, the force of 2 on 1 is going to point to the left. So, and it's going to be the same magnitude as this one. F of 2 on 1 over L, force per unit length, will equal mu naught I1, I2, but they're both the same, so I can just call them I over 2 pi r. And so that's what I'll have for the forces on each one of these things. Okay, and it's enough to make them stand out like that. Well, I'm supposed to figure out the current in each wire if they hang at an angle of 6 degrees with the vertical. So I'm going to restrain myself and just consider one of the wires and see how we can get this to work out. This would be a 6.00 degree angle. And we've got this thing standing down here. It's going to have, if I do a free body diagram just for that wire, and actually, let's imagine that we do have a length L of the wire. And so I'm going to bring the L back over here. This will be the force of 2 on 1 pointing to the right. Another force that's going to be acting here is mg down there, and it'll be a mass of this thing of length L. So they give me the mass per unit length on this thing. So with my length L, I should be able to do that. And then I'm going to have the tension in the wire up here, which makes a 6.00 degree angle. Huh. Well, I have a 3-vector problem. If I turn this into Newton's second law, I'll have the tension plus the force of 2 on 1 plus mg is going to equal 0. This is the sum of the forces equals ma, and in equilibrium, we don't have any motion going on. So that's what I'll end up with. And I can just draw a force triangle for this situation. I'll have, and this is, my angles aren't anywhere near correct, but that's okay. The 3 add together to give me 0. I have a 6.00 degree angle here. This is mg downward. This is the tension going in that direction. And this is the force of 2 on 1 here going in that direction. And I don't care about the tension. What I care about is mg and the force of 2 on 1, and something I can write. More paper here. These are being long problems here today as far as this goes. But the force of 2 on 1 divided by mg, that's the side opposite over the or the side adjacent that we've got here, is going to equal the tangent of 6.00 degrees. Now that force of 2 on 1, in this case, it'll be, oh, have I figured out? I guess I will have to take into account R to be able to figure this out. But I'll have, oh, I can write mu naught. I'm just going to write I squared because it says they're identical currents. And then I've got 2 pi R here, which I'm actually going to have to do a calculation to get that to work out. But that will equal mg times the tangent of 6.00 degrees. So I imagined this for a particular length of the wire. So I'd have an L in here as well. Now, the mass is going to equal that length times 0.0125, 0.0125 kilograms per meter. And what that means is I will have an L on each side of this equation. I'll have L mu naught I squared over 2 pi R will equal the M. I'll have L times that 0.0125. I don't know why I did that. That's a 1. Times G times the tangent of 6.00 degrees. Okay, that's kind of messy. But anyway, the L's divide out on both sides. So that's a little bit easier. And I squared will equal 2 pi R over mu naught times 0.0125 kilograms per meter times 9.81 meters per second squared times the tangent of 6.00 degrees. And I almost have this done. I haven't figured out R yet, but they're 4-centimeter long cords. And so if this is 4.00 times 10 to the minus 2 meters, and this is 6.00 degrees, then this would be 1/2 R. So 1/2 R over this thing would be the sine of 6.00 degrees. Sorry for the mess. Anyway, kick that over there, multiply both sides by 2, and R will equal 8.00 times 10 to the minus 2 meters times the sine of 6, whatever that is. And turn on your calculator first. let's see, and I would actually get out of this 8.36 times 10 to the minus 3 meters. So not much. This is going to be, let's see, that's just 8 millimeters. So pretty tiny is the actual separation between those things. So now we can solve this. Oh, and we'd want this whole thing to the 1/2. So I'm going to just plug in, well, I better be more careful. 2 times pi times 8.36 times 10 to the minus 3 meters divided by mu naught, which is 4 pi times 10 to the minus 7th. Oh, and this is going to be all to the 1/2 when I get done with it. Tesla meters per amp. And then trying to figure out how do I end up. That's meters. That takes care of the meters. I'll end up with an, oh, here's where the rest of it comes from. Okay, I'll have to monkey around with units here, but I'll have the 0.0125. This will give me a kilogram meter squared per second squared, which is a Newton meter. Yeah, that'll work. And 6.00 degrees, and I think that's all. Okay, I'm going to do a whole page figuring out the, well, not a whole page, but I'm going to have meters times amps times Tesla meters on the bottom times, this was kilograms per meter, I forgot that. And then kilogram meters, that's a Newton per meter. But a Tesla is a Newton per amp meter. So Newton per amp meter. Now that makes, oh man, let's see. Well, the meters go away. I'll have amp squared meter per squared on top, and I'll have meters squared on the bottom. This all ends up being amps squared, but I have to take the square root. So I'll end up with amps. Okay, and 2 pi over 4 pi is 1/2. So on the bottom, I'll just have 2 times 10 to the minus 7th, and that'll be to as many sig figs as I want. So I'll just keep 3 sig figs all the way through. So 8.36 minus 3 times 0.0125 times tangent of 6 divided by 2 times 10 to the minus 7th. And I actually get 5.00 times 10 squared for all of this stuff. Well, that's convenient, but I have to take the square root of that. So, to the 0.5. And I get 2.24 amps. That was a complicated problem. They brought in stuff from way back last fall, and many confusing things here. But a couple of things we got out of today is the force per unit length between parallel conductors, mu naught I1, I2 over 2 pi r, and that's what that happened to be. And they exert equal and opposite forces on each other. They either attract or repulse. So we got that. something we didn't get to today, which I was hoping to get to, was the magnetic field on the axis of a current loop. And here's the idea with that, you might have current flowing in something, and this is supposed to represent a circle on edge. And then we'd like to know what the magnetic field is, a distance X out here. So I might actually record an extra video on this. They do it in the book. I may have recorded it last year, actually, or 3 years ago, or 2 years ago, or whenever it was. But we can develop an expression for that, the magnetic field on the axis of a current loop. And starting Monday, we'll do some, maybe a couple of examples with this particular geometry. And then we'll introduce Ampere's law on Monday, which is something that can be used for a few situations in magnitude to determine the magnetic field. And it's similar to Gauss's law, where with Gauss's law, about the only times we could use it was for planar symmetry, spherical symmetry, and linear symmetry. And Ampere's law serves a similar role for magnetism. And we'll see how that works on Monday. But still in chapter 28, Ampere's law is. So we'll spend a couple of days on Ampere's law examples early next week. Okay, I think we're done for the day. Complicated problems today. So try to work those things out on your own and maybe try some example problems out of the book as well. And I'll